Hello, everyone. My name is Vojin, and I'm a PhD student in the LAMP lab at EPFL, supervised by Martin. And today I'll talk about Yin-Yang. And Yin-Yang is a framework that is made for programming DSLs in a simple way. And we'll see what does mean programming DSLs during the talk. So let's first define domain-specific programming languages. And here we'll a bit twist the definition. So we'll define languages that we care about, right? So in our context, a DSL is a programming language restricted to a narrow domain in order to improve both performance and usability, user-friendliness, right? So we don't care really about, in this talk, about DSLs that basically improve just productivity, for example, like Scala test. You write your tests in a neat, concise way, but you don't care about performance. So when you think about DSL in this context, so think about SQL, right? So when we look at this SQL snippet, for example, we'll see here that this language is really easy to read, right? So everyone can read this query. We'll take a name and email from Gmail and GitHub accounts, where usernames are the same, and the programming language is equals to Scala, and the level of the language knowledge is greater than 30, right? So trivial. Everyone can read it and understand. So it's very concise for its domain. And then SQL as well, because it's a very restricted domain, we can apply rules that we otherwise wouldn't be able to. So we, for example, know that natural joins are commutative and associative, and this can improve performance of our queries by a factor of 1,000. Okay. So when I say DSL, this is the DSL I talk about, not like XML or HTML or whatever else. Okay. So what is this DSL? It is for a DSL user. Essentially, this DSL should be user-friendly and fast. These are the two things. We'll simplify them into these two very concise things, right? And when you think about who uses the DSL, I want you to think about everybody, this guy, right? You want this guy to use our DSLs, right? Not some hacker or a scientist, like this guy, right? So it needs to be fast and beautiful, okay? So, however, with SQL there is a catch, right? And that's why I'm presenting here. So in order to build a SQL engine, you typically need to implement a parser, a type checker for SQL. Then you need to implement a debugger for SQL, the backend, and provide ID integration for all the different IDs and so on. And this is a monumental task, right? So essentially, when you think about a DSL author, basically I would like you to think about these guys, okay? So this is the work they need to do. Just imagine instead of lunch boxes that they have laptops, okay? So yeah. And that's why we came to the domain, to the concept called embedded domain-specific languages. And the idea here is to use work by the authors in this picture, one that did it once for a host language and reuse it for your restricted language. So reuse Scala or Haskell or some other language to embed a smaller language in it, right? And the first one that appeared was a direct embedding. It is a concept that essentially values in your DSL are directly represented by the values in your host language. So for example, in Scala, this would be Scala collections, for example. Think of collections, right? You map over int strings, so the values in the DSL, right, are the same as in the host language, right? And this is quite convenient. It's really easy to write this. These are essentially just fancy libraries, right? And they solve the problem for the DSL authors. You just write a fancy library, it does your stuff, but unfortunately, it's slow, right? So all these abstractions that we built basically create a lot of overhead. So think about this snippet. It basically sums up two sequences, right? And takes a minimum and a maximum. But when you carefully look at the code here, what happens is first we box all of the integers, right? And then we zip them into a tuple, which is again an object. Then we decompose this tuple, and then we like sum boxed integers, make a new boxed integer, and so on, right? And then we traverse twice in the bottom here, right? So this is horribly inefficient. It could be done in just a single while loop, right? So imagine our DSL user. Remember him. He wouldn't like this, right? Wait for like a second for a query to finish. No, right? So we need something better, right? And essentially we come to a concept called a deep embedding, right? So in a deep embedding, the values in the in the embedded language are symbolically represented by the values in the host language, right? So that the values in the host language essentially are the values in the embedded languages are data structures in the host language. So we kind of build an intermediate representation. And this is typically done by having a common supertype, for example, for all of the symbolic values. Here we call it, for example, rep of t. Last talk was about LMS, so you've seen it there. And then we build constant and a minus, and then we build some implicit operations that will kind of lift host language values into this symbolic representation. Okay, and then we can write code, right? However, this code now doesn't execute, right? It builds an intermediate representation. It builds this data structure of const of a minus of a 1024 minus 1. Okay, so but there is a catch again, right? So what happens when we debug this code, right? So we come to this line and we would like to execute step into it, right? Then it's a minus. You shouldn't be able to step into a minus. It's like a primitive operation, right? But when you step in, oh, you step in here, right? Building a data structure. Who cares about that, right? Imagine our DSL user looking at our internals, right? No, thanks, right? That's horrible, right? So, and then let's take this query language. It horribly resembles Slick, but imagine it's an imaginary query language, okay? And basically, here we say, like, query coffees, and if it's from Switzerland, right, we'll say it's a good coffee because George Clooney advertises it, right? And otherwise, it's like just the quality of the coffee, right? So, and this is what we get. Sorry, this is what we get. Don't know how to unpack any to T and so on, right? So don't even try to understand it. It will take you a day, okay? So again, think our DSL user. No way, right? He won't read this for an hour. No, he has to do some smarter things, right? So to summarize it in a table, look at it this way, right? Like deep embedding is not user friendly. These are just the two problems I presented. There is like a whole lot more, but they're extremely fast, right? Remember SQL, and the direct embedding is user friendly, but it's slow, right? So, and we here, but essentially, when we develop code, we don't really care about speed, right? We care about usability only, right? And then when we send our code to production, to the cluster or to a web server, that's when we care about speed, but we don't give a damn about code anymore. It's bytecode then, right? So essentially, but why don't we use this direct embedding while doing development and prototyping, and once we are done and tested, we just send it to a deep embedding, right? And this is how this project came to life, right? We essentially provide this automatic translation. Okay. So let's look at the code of the deep and the shallow embedding. Right. The whole idea is that they kind of should look the same, right? So on the left-hand side, we have a direct embedding of this imaginary query language, and on the right-hand side, we have it with implemented with Scala virtually, so that we don't get these ugly errors we got before. Okay, and essentially the code looks exactly the same. The only problem is that when you start modifying the code, make a type error or debug it, it becomes terrible, right? So it should be easy to translate one into another, right? So let's look what happens here behind the scenes, right? So this query from Scala virtualized, it essentially becomes something like this, right? It's a Scala component that hides all these wrap types and intermediate representations, right? Then this becomes a this query, right? Coffees is captured from the outside, so we'll have to lift it into our domain of our DSL. This becomes some kind of a wrap type of a coffee. So quite a bit of things happen when you unroll what's going on in the back, right? Again, a constant, we have to lift it. Equals is an intrinsic operation, right? So it'll have to become something like this. So, and so on, right? So, and this is essentially what we'll be doing in the next part, right? And then finally we have this good, which is again, we need to lift it, right? And yeah, So this is kind of what happens, and these things kind of destroy our usability, right? So that's why we want to automate it. And I'll show now how we basically do it, right? And we call this part of Yin-Yang like the core translation, because it's the essence, right? There is a lot of bells and whistles around, but this is the essence, right? So first step we take is we divided kind of the translation in two big parts, right? So to make it easier to digest, right? So the first one is language virtualization. And this was already done by essentially Adrian Morse and T.R. Krumpf in their paper Scala Virtualized. And in this paper, essentially, the idea is to convert all the language constructs of the host language into functions, right? So because you cannot do an if over a rep of T or any other kind of a type, right? So yeah, so that's the first part. But in addition, what we do here is we also treat all the functions, all the methods on any ref and any as essentially language constructs, because they exist on every type. They will exist on your nodes, right? So you cannot really, especially when they're final, right? You cannot really override them in some meaningful way. So in that sense, we also translate this, like hash code equals and so on. Okay? Simple. This is trivial, like 100 lines of code, nothing, right? And then the second part is the DSL intensification. This is the part when you take a block and splice it into the right-hand side, as we have seen, right? And so this is also very easy, right? So we just take a query and we convert it to a component, right? And then these objects, we just need to put a this in front. So strip off the prefix, put the this in front, we are done. Okay? Very simple. Sorry. Then constants that capture variables, again, right? We just add this lift method, right? Which essentially takes an implicit param, and that will do the lifting here, right? And then the DSL author can lift the different types in different ways, right? And what the translation will do, it will just simply add lift here, right? In this lifted place. And so on. Trivial, just identify constants. So essentially we split up translation in bits and pieces that can be useful individually, but then we apply them in a sequence and we get back to our embedding, right? And then finally the trickiest bit, I think, is the type translation. So you always, in your host programs, you can have types, right? You can ascribe values, you can ascribe functions, you can ascribe any expression. Yeah, you can ascribe any expression, right? And so you need to translate them as well, right? And we introduced this concept of type translation, basically. So, and I'll discuss just two. So we made this a configurable part that you can kind of build your own, right? But we provide the 3 or 4 most common ones. Okay, and yeah, let's take this simple one. So you say take type T if it's in the type argument position and just leave it as is. Don't care about that, right? And take any other T and convert it into a rep of T, for example, or R of T or whatever, right? Simple. So take any term, just rep of T, systematically convert, right? And voila, simple as that. 2 lines of code, in theory. So. And then, inspired by LMS, which is built for high performance, we took another approach. We said, let's treat these function types a bit differently, right? So if we have a function, basically we recurse on both sides. So we leave it as a functions, but convert trap types on the side. And yeah, and for the rest of the types, just as before. And what this gives us is essentially that every function becomes inlined at staging time. So as you compile your DSL, all the functions get inlined. But there is a catch for this, right? Essentially, you need to be careful about this error, about functions being in argument positions, because then things go wrong, right? And this translation fosters you to kind of prohibits you to put to create lists of functions or put functions in ifs and things like that, right? Because then you don't know them, you cannot inline them. So it kind of fosters you to statically know all your functions. Okay, and it's kind of interesting. You can just switch a translation and get a different behavior of your DSL, right? Just change a value. And what about correctness of the whole thing, right? So we had a correct direct embedding. Our DSL user that we love, right? He was writing his program. He was finished. How can we assure that once we translate, basically this will be correct, right? What would happen if we are done and our DSL user puts it into production and it doesn't work? Well, no, that's not acceptable, right? And luckily, of course, everything we do, Oleg has done before. So there is a paper by his, this is like finally tagless partially evaluated. And in this paper, he proves a part of our translation. And in a paper that's under submission, we proved the rest. Okay? So the translation is correct. So you take a direct embedding, translate it, and you'll get 100% correct thing, modulo bugs, of course. Except when your direct embedding has a richer interface. So imagine that in this query language, so imagine this is a direct embedding, and someone accidentally puts here a debugging thing saying, well, not really, right? And what would be the semantics of this once we translate? We would have to print line in a database, right? Because this goes to a database, and that's not possible, right? And what the translation would do, right? It would say this dot predef dot print line, not really, right? And voila, here is a type error, right? A deep embedding cannot have a print line. It's just simply cannot, because it cannot translate it to a database. So, and this brings us to another module of Yin-Yang, which essentially does language restriction, right? So what it will technically do, it will take every function that is applied, and for that function, it will make this synthetic call, okay? And try to type check it, right? And if the type checking fails, it will, in a fine-grained way, give you an error message saying, saying predef is not defined predef is not defined in our query DSL, right? And it will be a user-friendly message, a message our DSL user would like to see, okay? So, yeah, and this happens even in the direct embedding part, right? So our DSL user always gets the nice messages. So let's now look at Yin-Yang, how does one apply Yin-Yang, right? So basically, it's very simple. So a DSL user, you've seen, he just sees this. And unlike current DSLs, you essentially have to write your DSLs in scope. So you say, this is my new language, right? And this language might be restricted, might not have ifs, or might not have whiles, or anything that we restrict by language restriction, okay? And unlike others, like Slick or LMS, where you can kind of intervene your programs with the rest, so kind of wrap types, you look at the program and you don't know what's wrap and what's not wrap type. Here it's like explicit. You say, this is my language, right? So query, period, right? The boundaries are explicit. That's it. That's for a DSL user. And what a DSL author needs to do is basically all these transformations are nicely packed up in a pipeline in this object YY transformer. And all you need to do as a user is make a macro query, right? And say, well, it's just a transformer that takes, this is a DSL name, and this is a type transformer, period. Okay? So pretty simple. Okay? So, and then once we built all of this, it was some work. We kind of decided to experiment a bit, and we said, like, what DSL would we like to use, right? And let's take an existing DSL that people have troubles with type errors, right? And we said, let's take a Slick. Slick is widely used. It's an interesting DSL. It wasn't really designed for Yin-Yang, but yeah. For those who don't know, Slick compiles basically queries like written in a functional programs into efficient SQL, as we've seen the coffee example, right? And yeah, it's also based on wrap types. They're called columns and wraps. It depends, but basically it's kind of wrap types. And so the first thing we did, we said, well, you know, Slick has all these implicit conversions on, you need to read a lot to understand them, right? Jump over them. So kind of it's not, this translation will not apply anymore, right? It's not consistent, right? So we had to build something like a new interface, and that's what we did. This is a new interface, 70 lines of code, I think. Nothing special, but it's really simple. No implicits, no magic, right? And we don't provide the implementation for this. For debugging, because kind of databases have different semantics than Scala, so we didn't even bother implementing, okay? And then, unfortunately, because it wasn't built, we just built a little wrapper, right? So we said, well, you know, width filter, you translate it like this, flat map to this, so we essentially manually put all these implicits that are ugly into the backend, right? And what we got is that the master student was doing this in 2 months, in less than 2 months, in less than 1,000 lines of code, I think. He got practically all tests of Slick passing. Right? And now, yeah, you can just write Slick, no wrap types. And a funny consequence, because also we do caching, but I don't cover it here, we got also speedups, right? So queries basically in Slick, if you don't do parameterized queries, queries compile every time you run them. And here we have scopes that cache the code, so basically it's much faster, right? And yeah, this was a pleasant experience, right? And if Slick was built for Yin-Yang, you could throw away all of these implicit conversions and type computations and all these things and just systematically translate, right? And it would be basically a few days' work. Okay. So let's look at what happens when we want to construct a new DSL now, right? So Slick was existing, we used it with the LMS. LMS was existing. Let's see a new DSL. Well, the problem here is that you have a direct embedding and you have a deep embedding, and they need to coexist in synchrony, right? And we know what happens with this. This is typical code duplication. So if someone changes a deep embedding, he breaks the kind of change, needs to change the behavior of the other, and eventually we would get bugs, right? So then what we decided is, well, we have the bodies, we have the methods, right? We know kind of from the direct embedding how the deep embedding should behave. So why not do something like just like this, right? Say, we want to generate a deep embedding for this, right? And then we do, right? We just, out of this, we build this ops and all this like boilerplate. So this is an interface. Then we also generate all the case classes. So essentially, you don't, as a DSL author, you don't have to worry about methods and vals and objects and nested objects and all this stuff. You just, it's your domain, right? So you care about, is it a big decimal new or a big decimal plus, and so on. You don't care how it was generated, okay? And then code generation as well. So we take the bodies of this method, translate them with Yin-Yang, and build code generation again, right? Unfortunately, back then, yeah, when we built this, there was no runtime kind of reification of trees, so we weren't possible to kind of splice trees, so we had to generate back Scala code, which is funny, like a generator for code generator, right? And finally, why we came to the deep embedding in the first place is we want optimizations, and we kind of make placeholders and say when you have a big decimal plus, you just add some domain knowledge. For example, if you sum something with a 0, you should ignore that. Or if you sum two constants, you should ignore that, right? And so on. And then you can go further, like query ordering and so on, right? But let's take for this simple example. And yeah, let's take it for a spin. So this will be a DSL author. He uses like a text editor, right? Like Eclipse won't work, right? So, and I built this essentially, yeah, I already placed this big decimal DSL here so that we don't waste time. And what do we want to do is basically say just at deep, right? We design it and it's just stupid for the purposes of demonstration. We just basically wrap the Java big decimal, which is Scala big decimal does the same, okay? And we say at deep, and then let's see if it compiles. Good. So and then what we want to do is now we have this thing that is essentially this generator is a kind of a compiler plugin that will compile the code, look at the annotations, the deep annotations, and essentially generate the embedding based on them, right? So I call it embed, I think. Voila. And now if you look here, it's called the same. It's just in this folder lifted. We'll basically get all of this, right? Generated. So code generation, case classes, and the interface. So and all you need to do is basically put your optimizations here. That was one thing, and then you remember this like Yin-Yang for newbies, right? We need to define basically this transformer here. I already put it in place, so that we use time. So we just basically say new YY transformer, C.type, and so on. And basically, it's a wrap transformer, and this is an unfortunate artifact that by name, named arguments don't really work with macros, so I have to put this none and map, but otherwise you wouldn't have to put it there. It's a bug, basically. So yeah, and that's it. And now we're practically done. So let's take this for a spin, right? Let's sorry, not that Eclipse. So now we are becoming a DSL user. We are done. Sorry, I didn't publish this. Just so. Okay. So not that Eclipse. So and now we are a DSL user. So what we import decimals and maybe we have a main function. So what we would like to do basically here is let's make some value which is essentially equals big decimal of let's say 41.9999. Why not? And the value v2, for example, which is equal to 0. This should be good, I think. Yep. And let's say result is equal to v1 plus v2, just for the demonstration, and let's say let's print the value of this result. Okay, and run this code. Voila, we got 42. These are big decimals, right? So we can do arbitrary precision, and good. So this is a direct embedding. You can even use it without the scope, basically. But let's change this a bit. Let's now how a DSL would look like, right? So we would do a big decimal here, and voila, you would run. And what happens here is just only language restriction kicks in, right? So nothing else, basically, because you just say, this is a prototyping mode. This is a mode for our user. And in this mode, you can do whatever you like. Basically, the macro just takes the trees, checks if they're fine in the deep embedding, and puts them back, right? So let's debug this function, right? So we can, for example, step over the code. Fine, yeah. Inspect the values. Now it's a big decimal, so yeah, here it is, right? Inspect the values, go in, everything you would do typically, which you cannot really do with deep embedding because you cannot step through SQL, you cannot step through other DSLs, and this is amazing here. And yeah, and let's run it to the end, for example, and voila, we're done. We have the same result. Just a moment. Voila. So, and now let's come to this point when we are done with our development. And no, let's first try to put something inside. So let's say we want to use a hash code of this instead of a result, for example, right? And we'll say, well, not really, right? We have an error here that says language construct, hash code, we treat it as a language construct, is not really supported by our DSL, right? So, and the same applies for others. If print line and so on, it will say just, sorry, not possible, right? And then let's try to do some other stuff. So let's what can we do? We can, for example, do a funny optimization. Let's try to say basically if we have let's run it first in production. Let's say we are done with the development and let's run this DSL in production. So what we'll do is we'll change the properties of this project and we'll just change a single compilation file here. And we'll say macro settings, and we'll say embed, and this will essentially go to the compiler, and the macros will be able, the Yin-Yang macro will be able to read this command. And now when we run, I configured this in a way that essentially that it shows what it generated on the way, right? So it's not anymore the code we had. It's like the deep embedding of DSL. So what will happen? The LMS, the lightweight modular staging that we use here, will basically generate this class that for each thing generates a new big decimal apply and so on, right? So it kind of regenerated itself. And what can we do now is we have domain-specific knowledge, right? So we can go here and in our lifted big decimal, we can do like things like this, for example. Say, right, so say, for example, we have a self, and we have a left-hand side. And we would say, we would like to do things, I don't know, let's say first this is a default case, so if it doesn't match our things, do nothing. But for example, say, so if self, and then here we have, we say, this is a plus, right? We want to define a constant 0. So how are we going to do that? It's a case class of an apply. So we'll just match on an apply, right, of a const of a 0, right? And in this case, what it will return is just the self. So it says addition with 0 doesn't really make any sense. But now on the domain of in the deep embedding, right? If it's something that the compiler otherwise couldn't be able to optimize. And if we publish this, if I type checks, does. So with and do it to the end of the talk. So if we publish this, we'll get the same thing, right? Because here it's a 0, 0, 1. But if we change this to 0, right? So here we need a value. If we, yeah, it's gone, right? And so this is just a simple example, but you can build transformers, you can reorder all your code, you can basically build a whole SQL engine in, right? So you give to arbitrary pieces of your code, you kind of give domain-specific knowledge, okay? And that's it. So you're a DSL user, you basically write your code, you enjoy it, you're done, and you say, flip the switch, goes to production, right? That's simple. So back to the presentation. So what are the takeaways here, right? So you as a DSL user, you now finally can kind of use embedded languages. So before SQL, there's not so many external languages. They're extremely hard to build, right? And users don't really like deep embedding of languages. Some do, but mostly not, right? So now users, it's possible to have more DSLs now, deep embeddings, right? And for example, for matrix operations, linear algebra, and so on, right? And then for the DSL author, it's tremendously easy to build them. So you essentially write your programs like a library, and you say, I want to embed this library. That's that simple. Write your optimization rules, and you're done. If you change your direct embedding, the changes propagate to the deep embedding. So you don't have to worry about it. You just need to worry about optimizations and the direct embedding. Okay? And the question is this it? Are we there yet? And I would say there's a missing bit, right, to make this guy happy. And that is essentially what we need is custom type errors, right? Because still in the deep embedding, we know Scala test, for example, right? So in it, you can still get some nasty errors, right? Although it's a direct embedding. So we need kind of a way to make this possible, to make this guy happy. And Hubert from our lab is working on that, and I really hope this is going to get in. And the team, finally, I would like to thank everyone. So it's basically Sandro, who basically knows all the theory, and whenever he speaks, your brain explodes. And Amir, who is like a bulldozer, he does whatever is required. And Vladimir and Vera, which are amazing team members. And yeah, that's it. Thank you very much. Yes?
With any of these kind of separations of code that you write and code... Oh, there we go. Any of these separations of code that you write versus code that runs in production, they give you a unique problem, which is debugging when you screw up the code that's running in production. What's the environment like for that? And do you have any recommendations or tools that are useful for tracking down when you generate incorrect code?
Yes. So what we have for this, very good question. Things eventually go wrong, right? And what we have for this is a concept of source context. So essentially, I didn't show it in this example, right? Because it's a part of Scala virtualized, and we are kind of moving this to regular Scala. So with every operation, we also track the source context, and it goes all the way to the code generation. So you can basically for each generated line of code, you can track where it came from the back. So you we have even a debugger, but this is all in research state, right? So it would require some work to make it work, but yeah, you can map directly. So you click on a line, you see what was generated from it, and so on, right? But very good question. Yeah.
So you have to put your own optimizations in the generated deep code. So if you were to change the direct code and you regenerate the deep code, do your optimizations stick around?
Yeah. So let's do this, right? So actually, here I made a mistake, right? So in our demo, it wouldn't work because I put it in a same file. All right, but the thing is that is a cool part here, that we generate these traits, and you can this opt trait should go essentially in a different, basically in a different file, and then you shouldn't really change that one, regenerate that one, and then everything else will just stick around, right? So yeah, right. That's the cool thing, that we use the kind of cake pattern here for this. Right? There's a question here.
So we go back to the pattern page?
Which one? The optimizing one?
Some of the, this one.
Yes.
Is it possible to express something like this with quasi-quotes? Because I imagine when it becomes more complex, it also becomes more unwieldy to write this with case class.
Yeah, a very good point. It would be possible, but I'm working on that now, basically. So we can use Yin-Yang, but for now only for single line quasi-quotes, right? If you have multiple lines, the thing is that the point of Yin-Yang is that some of the things get very simplified for the user. So if you, as a DSL user, you would to get to this contextual information, you would have to do all the messy things we do, go through the objects, nested objects, extract all the stuff, right? So we remove this, but we also lose some information. So quasi-quotes don't map, like a syntax doesn't map directly to the case classes anymore, right? So in that sense, I'm still thinking what to do. Probably, I'm not sure. I'll see, but for now, not. Good question.
One large advantage of embedding DSLs is that you can simply compose them. So now when putting this annotation around restricting the language, I guess you cannot just use other DSLs inside of that scope. Are there means to kind of lift one language to another by manually specifying, I don't know, implicit conversions to trick around that? So can you compose DSL?
Yeah, it's again, very good question. So you can in some cases, right? So DSLs don't compose always, but in most of the cases you can. And what we do for now is this deep won't track transitive dependencies. You've seen that big decimal doesn't depend on anything, right? But theoretically, you could basically, for every subcomponent of big decimal, you could generate a specific set of cakes, and then finally you would just mix them all together, right? So and I didn't demo this because it's not ready yet, and we do this manually for other DSLs. So we basically we handwrite the script what is a dependency for a DSL, for example, for a big decimal here, right? And the core of our DSL engine is always a dependency, right? So this is like while loops, ifs, and so on. Like the core is always there, but then for the rest we hard code.
But do then the DSLs have to be prepared in advance to be composed?
Yes, because macros, I hope, that's why on this book is what it was saying, looking forward to Scala meta, right? We want trees in jars, that's what we need, right?
Okay, thank you.
Yeah.